What's going on, everybody? Got another video here for you. This is implicit differentiation and related rates. So we'll learn how to do implicit differentiation, we'll work some word problems, and then we'll do a couple of related rate problems. All right, so implicit differentiation. Suppose an equation defines y implicitly as a differentiable function of x. I will explain in a little bit, in just a minute when we get to the example, what an implicit function is. So to find the derivative, to find dy dx, differentiate both sides of the equation with respect to x. Remember that y is really a function of x, and use the chain rule when differentiating terms containing y. And then once you do that, you solve the differentiated equation for dy dx. All right. So before we find the derivative of this, let's just kind of talk a little bit about what we just read. All right, so notice it tells you when you're taking the derivative of the y term to use the chain rule. So forget about the problem right now, this example. Don't even worry about it right now. So do you remember what happens when you have something like this and you want to find the derivative? Well, the derivative is dy dx is equal to 3 times 2x squared plus 1. That's a plus 1. I forgot to put the plus 1 squared. So remember, the 3 comes down, subtract 1 from the exponent, and then it's times the derivative of what's in the parentheses here. So that's times the 4x. Okay, that's the chain rule. And what they're telling you up here is, let's suppose you have something like y cubed, okay? So the derivative of this is 3y squared, and you can think of this y as being in parentheses and do just like we did up here. So remember, the 3 comes down, subtract 1, and then times the derivative of what's inside the parentheses. So the 3 comes down, subtract 1 from the exponent, times the derivative of this y. Well, what's the derivative of y? It's dy dx. See, just like we did here when you have just y equals. Well, you're taking the derivative, so that's what? Dy dx. And I know in some problems we use y prime equals 3 times 2x squared plus 1 squared times 4x. We use the notation y prime instead of dy dx. Okay, for the implicit differentiation here, we're going to use dy dx. You could use y prime, but we'll just use the dy dx. All right. So that's what this is saying. Okay, and then once you differentiate the entire equation, then you're going to solve for dy dx. And now let's talk a little bit about an implicit what an implicit equation is. So this right here, notice this right here, we can't really solve this. We can't solve this for y. So you're not going to get this in terms of y equals something. Okay, you know, like you've had in the past, you've had y equals something like 2x minus 1. Okay, that's what you're used to seeing. But we can't get this y equals like this. So we use implicit differentiation. All right, so let's find the derivative of this thing. So we differentiate each term. Okay, all the same rules apply. Okay, they all apply, just like what you've learned so far. Okay, and the easy way to look at this is you take the derivative just like you normally do, but when you take the derivative of the y term, you just tack on a dy dx at the end. So let's work this problem and I'll show you. All right, so notice here this first term here. Notice we've got two functions here. We've got an x squared and we've got a y. So that means we have to do the product rule there. Okay, the x squared, that's our first function. The y is our second function. So the product rule says the derivative of the first function, which is 2x, times the second function, which is y. So I've got the derivative of the first times the second, plus the derivative of the second. Well, what's the derivative of y. It's 1. And then remember, tack on that dy dx. Let me write that a little better. Dy dx. Okay, so I've got the derivative of the first function times the second function plus the derivative of the second function, that's the derivative of y, times the first function, so times x squared. So that's the derivative of this first term right here, all of this right here. Okay, and then plus the derivative of y squared. What's the derivative of y squared? Well, that's just 2y. Power rule is all we're using. But remember, we took the derivative of the y term, so we tack on that dy dx. Okay, just remember, you do the same rules that you've been doing. It's just when it's the y term, you add that dy dx at the end of it. Equals, and then the derivative of x cubed is 3x squared. And now we want to solve for dy dx. So I get x squared dy dx plus 2y dy dx equals 3x squared minus 2xy. The 2xy, I moved it to this side over here. Now, notice here how I have a common factor of dy dx. So I can factor out that dy dx, and I'm left with x squared plus 2y equals 3x squared minus 2xy. All right. And then I divide both sides by the x squared plus 2y. So I get dy dx is equal to 3x squared minus 2xy over x squared plus 2y. And there's my answer. All right. So you can see it's not that bad. All right, so let's look at this one. Find the slope of the tangent line to the circle x squared plus y squared equals 25 at the point 3, 4. And then they also want to know what is the slope at the point 3, negative 4. So what did it ask us to do? It asked us to find the slope of the tangent line, right? Well, how do you find the slope of the tangent line? You take the derivative and then evaluate the derivative at the point. All right. So let's take x squared plus y squared equals 25 and then differentiate it. So that's going to be 2x plus 2y, and then don't forget dy dx, all right, equals derivative of 25 is 0. So derivative of x squared is 2x, derivative of y squared, the 2 comes down, subtract 1, so you got 2y, and since I took the derivative of the y term, I tack on that dy dx. And now I solve for dy dx. So I get 2y dy dx equals negative 2x. Divide everything by 2y. So I get dy dx is equal to negative x over y. All right, so there's my derivative. Now they want me to find the slope at the point 3, 4 and the point 3, negative 4. So dy dx evaluated at the point 3, 4. Okay, I'm going to do this one first. So I'm just plugging it in. That's going to be negative. X is 3, y is 4. Remember, that's your x coordinate, and that's your y coordinate. Same thing here. This is your x coordinate, that's your y coordinate. And then dy dx evaluated at the point 3, negative 4 is negative 3 over negative 4, which is positive 3/4. And there's your answer. All right. So you can see it's not too bad. All right. So what do we have here? Find all points on the graph of the equation on that equation where the tangent line is horizontal. Does the graph have any vertical tangents? Okay, so let's write our problem down. X squared minus y squared equals 2x plus 4y. All right. So let's see what we've got. How do we work this? Well, it says find all points on this graph where the tangent line is horizontal. So basically what we want to do here is find the derivative of this. Then we need to set it equal to 0 and solve. Okay? Because once we find the derivative, isn't that the slope of the tangent line? So once we find the derivative, we take that derivative, which is the slope, and we set it equal to 0. Because that's the slope of a horizontal line, right? And that's what they want to know, where the tangent line is horizontal. So let's find the derivative. So I've got 2x minus 2y dy dx equals 2 plus 4 dy dx. See, I used all the same rules that I've been using to find derivatives. It's just when I took the derivative of the y term, I tack on that dy dx. So now we got to solve. So let's see, what would be the best thing to do here? Probably do 2x minus 2 equals 4 dy dx plus 2y dy dx. So I move the 2 over here and I move this term over here. And so that's going to give me 2x minus 2 equals dy dx times 4 plus 2y. And then divide both sides by this. That's going to give me dy dx is equal to 2x minus 2 over 4 plus 2y. All right, so here's my derivative. So now what we want to know is, when is the tangent line horizontal? So I want to know, when is this derivative here 0? So let's just let's come up here and let's just write this again. We've got dy dx is equal to 2x minus 2 over 4 plus 2y. So I want to know, when is this 0? Well, when is a fraction 0? It's 0 when the numerator is 0. So this is going to give me 2x equal 2, which means x is equal to 1. So I have a horizontal tangent when x is equal to 1. But it does want the points, right? It wants the points for where the tangent line is horizontal. So I need to take my x value of 1, and so that's going to give me 1 squared minus y squared equals 2 times 1 plus 4y. So I took the 1 and I plugged it into my original equation here for x. And so that is going to give me, let's see, if I move that over there, move this over, that's going to be 0 equals 1 plus 4y plus y squared. So let me just write it over here. Y squared plus 4y plus 1 equals 0. And so what I have now is I have a quadratic equation to solve. And so I've got y equals negative b plus or minus the square root of b squared minus 4 times a times c all over 2 times a. Quadratic formula, right? Remember, quadratic formula is negative b. Let me write that in a different color. That's negative b plus or minus the square root of b squared minus 4ac all over 2a. Okay, that's your quadratic formula. And so once I punch all that into my calculator, I'm going to get y is equal to negative 0.27 and y is equal to negative 3.73. So I have a horizontal tangent at the point 1, negative 0.27, and 1, negative 3.73. That's where my horizontal tangent lines are. Where my tangent lines are horizontal at those 2 points. And then they want to know, is there any vertical tangents. Well, when do we have a vertical tangent line? Well, that's when it's undefined. That would be here at when 4 plus 2y is equal to 0. So if I take the 4 plus 2y equals 0, that's going to give me 2y equals negative 4, so y is equal to negative 2. All right, so what I'm going to do now is I'm going to take this. Let me bring this down here so we can see it. We're going to basically do the same thing. There's my equation. So now we need to take the negative 2 and plug it in for y. So I get x squared minus negative 2 squared equals 2x plus 4 times negative 2. So x squared minus 4 equals 2x minus 8. And so I get x squared minus 2x plus 4 equals 0. All right. Now we need to solve this for x. So I'll use the quadratic formula. I'll tell you what, we use the quadratic formula on that one. Let's come up here. Let me write it up here. Instead of using the quadratic formula, let's complete the square on it. Okay? So you'll see both of them. Most all students can do the quadratic formula, but most of you struggle with completing the square. So let's complete the square. But keep in mind you can use quadratic formula. So I've got x squared minus 2x equals negative 4. Remember, move this over. And so I half the 2. Half of 2 is 1. 1 squared is 1. So I add 1 to that side. So x minus 1 squared equals negative 3. Oh, look at this. X minus 1 equals plus or minus I square root of 3. I get an imaginary solution. So the denominator will never be, well, the denominator is not going to be 0. Okay, at the point where y is negative 2. Okay. All right, so there's no real solution. Okay, so that means that this graph has no vertical tangents. So no vertical tangents. All right. So, I mean, these are good problems, but, the main point of them, I mean, we're doing some applications, word problems, stuff like that. But notice we're getting different functions to practice on doing implicit differentiation also. All right, so let's look at this. So it says, suppose the output at a certain factory is Q equals, let's write that down because I'm sure we're going to need it. Q is equal to 2x cubed plus x squared y plus y cubed units, where x is the number of hours of skilled labor used and y is the number of hours of unskilled labor used. The current labor force consists of 30 hours of skilled labor and 20 hours of unskilled labor. Use calculus to estimate the change in unskilled labor, y, that should be made to offset a 1 hour increase in skilled labor, x, so that output will be maintained at its current level. All right. So here we go. Let's see what we've got here. All right. So right now it says the current labor force consists of 30 hours of skilled and 20 hours of unskilled. So basically what we're going to do is we're going to find this derivative, and we're going to need values to plug into everything except what we're actually looking for. Okay, so let's go up here and let's look at the information that they give us. All right, so notice they tell us that the labor force, the current labor force consists of 30 hours of skilled labor and 20 hours of unskilled. Use calculus to estimate the change in unskilled labor, Y. So right there, they're telling us that Y represents the unskilled labor. Okay, so that means X is going to represent the skilled labor force. So the X is 30, Y is 20. And what other information do they give us? Let's see, they tell us that unskilled labor Y, that should be made to offset a 1 hour increase in skilled labor. So that 1 hour increase, so that's the change in skilled labor. So that's the change in X. So they're telling us that dx dt is equal to 1, and we're wanting to find dy dt, right? See, they're wanting us to use calculus to estimate the change in unskilled labor Y. And then we're also going to need some value to plug in for Q. Okay, and we're going to maintain that. Okay, we're going to maintain the current level of output. So how do we do that? Well, what's the current level of output? Well, it's 30 hours for skilled and 20 hours for unskilled. So we can take Q is equal to 2 times 30 cubed plus 30 squared times 20 squared plus 20 cubed, right? We just plug all that in, and that's going to be 80,000. Whoop, let me put the zeros. 80,000 units. Okay. All right. So now we have us an equation. We've got 2x cubed plus x squared y plus y cubed equals 80,000. So now let's take the derivative of that. So that is going to give us 6x squared plus, now here we have to use the product rule. So it's the derivative of the first function times the second function plus the derivative of the second function, dy dx, times the first, plus, and then the derivative of y cubed is 3y squared times dy dx equals, and then the derivative of 80,000 is 0. Okay, so now we solve. So we're going to get x squared dy dx plus 3y squared dy dx equals negative 6x squared minus 2xy. So these terms without the dy dx, I just move to the other side. So we got to isolate the dy dx. So I get dy dx times x squared plus 3y squared is equal to negative 6x squared minus 2xy. And so that is going to give me dy dx is equal to negative 6x squared minus 2xy over, let's see, what is that? X squared plus 3y squared. Okay? And see, this is what we wanted. We wanted dy dx, right? And so now I'm going to take the dy dx and I'm going to evaluate it at what? Well, what do I have to do? I've got to plug in an x and a y value, right? And x is 30 and y is 20. And so this is going to be when x is 30 and y is 20. And so this is going to give me negative 6 times 30 squared plus 2 times 30 times 20, not plus, minus, and then that's going to be 30 squared plus 3 times 20 squared. And this is going to give me negative 3.14 hours. All right. So what does that mean? See, we want to maintain that current level of production. Okay, we want to maintain the current level of output. So if I increase the skilled labor by 1 hour, what do I have to do with the unskilled so I have the same level of output of that 80,000 units that we calculated up there? Well, what that means is to maintain the current level of output, unskilled labor, okay, because remember, the skilled labor we're increasing by 1 hour. The unskilled labor, I have to decrease that by 3.14 hours to offset the 1 hour increase in skilled labor. All right. All right, so moving right along. So here we've got some related rate problems. We've got about four of them to work. So let's see what we've got here. They shouldn't take too long. They might, but it's all good. We enjoy doing this stuff. A procedure for solving related rate problems. Draw a figure, if appropriate, and assign variables. Find a formula relating the variables. Use implicit differentiation to find how the rates are related, and substitute any given numerical information into the equation in step 3 to find the desired rate of change. Okay, so it's I guess kind of like what we did up here. Okay. All right, so let's see what we've got. It says the manager of a company determines that when Q 100 units of a particular commodity are produced, the total cost of production is C $1,000, where, and so we've got C squared minus 3Q cubed equals 4,275. And then it tells us when 1,500 units are being produced, the level of production is increasing at the rate of 20 units per week. What is the total at this time, and at what rate is it changing? All right. So I tell you what, let's do this. Let's find the derivative, and then let's determine what we're trying to find. Okay, let's determine what we're trying to find and all that good stuff. Okay, and we'll go about how we get the information of the variables we need numbers for to plug in. Okay, so let's go ahead and find this derivative here. So that's going to be, now we're taking the derivative with respect to t for related rates, the derivative with respect to time. So I've got 2c dc dt minus 3q squared dq dt equals 0. All right. Now let's kind of talk about this for just a second. What are we actually trying to find? Are we trying to find dc dt? We're trying to find dq dt? Are we trying to find qc? What are we trying to find? Well, let's come up here. It says the manager of a company determines that when Q 100 units of a particular commodity are produced, so Q represents the number of units, the total cost of production is C $1,000, where C equals that. When 1,500 units are being produced, the level of production is increasing at the rate of 20 units. Okay? So what are we actually trying to find here? Okay? So the level of production is increasing at that rate. What is the total at this time, and at what rate is it changing? So they're wanting to know the total. They're talking about the cost. Okay? What is the total at this time, and at what rate is it changing? Is the cost changing? All right? So that tells me I need to solve this for dc dt. So I've got 2c dc dt equals 3q q squared dq dt. And then divide both sides by 2c. So I get dc dt is equal to 3q squared over 2c. Okay, and times dq dt. So there's my derivative. All right, so let's see. I think maybe based on the things we've got to find, we might answer both questions as what is the total at this time. So what's the total cost at this time? Okay. And then they want to know at what rate is it changing. All right, so I actually need to know, so for the total cost, I need to know what C is, right? I need to figure out what C is. Well, can I do that? Yeah, because it tells me when Q is 1500, right? So that means I just plug that in for Q and I can solve for C. And look at this, I need C anyway to plug in. Okay, so let's do that. So I've got C squared minus 3 times, and then what does it say? It says the manager of a company determines that when Q 100 units of a particular commodity are produced, so that means Q is 1500, so that's going to be 3 times 15 cubed, right? Because it says that Q represents hundreds of units. So that means I've got to take this decimal and move it 2 places to the left. All right. And that's going to equal 4,275. So I've got C squared equals 4,275 plus 3 times 15 cubed. So C squared is equal to 14,400. So C is plus or minus 120, right? C is plus or minus 120. But we know we're just going to use the plus. I'll go ahead and write it. Or C equals negative 120, and we know we're not going to use that one. All right. Now, let's look at this. So here's the answer to, there's your answer to what is the total cost at this time. Okay. All right. So now we want to know how fast is the cost changing. So I've got to plug in a number for C. So I've got C is 120, Q is 15, right? See, they give me that. Q is the 1500 units, so I'm going to plug 15 in for Q. And then I've got C and Q covered. Now I need dq dt. dq dt, well, what is that doing? Is increasing at the rate of 20 units per week. So that is equal to 0.2. So remember the 20 units, that's in hundreds. So I've got to move it back. Q represents hundreds. And so now I've got dc dt is equal to 3 times 15 squared over 2 times 120 times 0.2. And that is going to give me 1.6875. So what does that mean? All right. So the cost of producing 1,500 units is what? $120,000. That's what we got here for C is 120. And remember, C is $1,000. It's in thousands. So I've got to put it in thousands. And at this level of production, the total cost is increasing. So total cost is increasing at the rate of $1,687.50 per week. So I have to put that in thousands. Okay, and there you go. That's what they're wanting. All right, let's look at this one. All right, it says a storm at sea has damaged an oil rig. Oil spills from the rupture at the constant rate of 60 cubic feet per minute, forming a slick that is roughly circular in shape and 3 inches thick. How fast is the radius of the slick increasing when the radius is 70 feet? And then B, suppose the rupture is repaired in such a way that the flow is shut off instantaneously. If the radius of the slick is increasing at the rate of 0.2 feet per minute when the flow stops, what is the total volume of oil that spilled onto the sea? All right, so this is the volume, okay? And not necessarily the volume of a, well, you wouldn't say volume of a circle, you would say area of a circle, but this is the volume of a cylinder, right? I mean, isn't this oil slick a cylinder? It's a circle, and it has a height to it of 3 inches. Okay, so it's just a real short cylinder. So I know I have volume is equal to pi r squared h, right? And I know that h equals 3 inches, which is equal to what, 3 over 12 feet, which that's 0.25 feet. Okay, that's the height. Okay, it doesn't say anything about that height changing. And see, they tell us it's 3 inches thick. But notice the other information they give us. They give us 70 feet, 0.2 feet per minute, 60 cubic feet per minute. So we've got to put the 3 inches in feet. Okay. All right. So what do they? Let's get some information that they tell us. They tell us that dV dt is 60, right? See, the oil spills from the rupture at the constant rate, so that's the rate of change of the volume is 60 cubic feet per minute. And let's see, what else do they want to know? They want to know how fast is the radius of the oil slick increasing. So we're actually wanting to find dr dt. That's what we're looking for. And they're wanting to know that when r is 70. When r equals 70. So I've got V is equal to 0.25 pi r squared. So what I did, since the height, the thickness or the height of that oil spill is constant, it's just 3 inches thick. It doesn't tell us that that thickness is changing. So I replaced the h with the 0.25. And so I've got dV dt is equal to 0.5 pi r times dr dt. And notice they're wanting us to find dr dt, right? You see that? So we need to solve for dr dt. All right, so I'm going to get dr dt is equal to 1 over 0.5 pi r times dV dt. And now we plug everything in. So I've got 1 over. So I've got dr dt is equal to 1 over 0.5 times pi times 70. I plug the 70 in for r, times 60, which is the dV dt, and that is going to give us 0.55. So what does this mean? When the radius is 70 feet, it is increasing at about 0.55 feet per minute. Okay, that's how fast the radius is increasing when the radius is at 70 feet. All right, part B. Suppose the rupture is repaired in such a way that the flow is shut off instantaneously. If the radius of the slick is increasing at the rate of 0.2 feet per minute when the flow stops, what is the total volume of oil that's spilled onto the sea? All right. So this is part B. That was part A up there. So I've got 60 is equal to 0.5 pi r times 0.2. Okay, so let's look at that. All right, so let's look up here. So we can compute the total volume of oil in the oil spill if we know the radius of the slick right when it stops flow. Okay, and since dRdt is 0.2 feet per minute when the flow stops, okay, we can use 60 as 0.5 pi r times 0.2, and we can take this and solve it for r. So this is going to give me r is equal to 60 over 0.5 pi times 0.2, which that gives us 191 feet. And so to find the total volume, we've got the volume. Remember, volume is 0.25. Okay, that's your thickness there. All right, so that's going to be 0.25 pi times 191 squared. And that is going to give us 28,652 feet. Not feet, cubic feet. All right. So there you have that. All right, let's look at this one. I think we only got two more left, so just hang in there. Just hang in there. All right, it says a lake is polluted by waste from a plant located on its shore. Ecologists determined that when the level of pollutant is X parts per million, which we'll abbreviate ppm, there will be F fish of a certain species in the lake, where F is equal to this. So we're going to need that. F is equal to 32,000 over 3 plus square root of X. When there are 4,000 fish left in the lake, the pollution is increasing at the rate of 1.4 parts per million per year. At what rate is the fish population changing at this time? All right, so basically we need to find the derivative of this, right? Let's find the derivative. So we have df dt. This is quotient rule, so derivative of the numerator times the denominator minus the derivative of the denominator, so that's going to be 1 over 2 square root of x. Now, if you haven't seen any of my other videos, I have a shortcut for finding the derivative of a square root. So the square root of x, okay, just come over to the side. Well, derivative of 3 is 0. Derivative of square root of x. Whenever you're taking the derivative of a square root, every time, 2 times whatever that square root is, that goes in the denominator. And then the derivative of what's underneath the square root goes in the numerator. And so that's where that comes from. And that's going to be times 32,000. All right. And that, well, let me do this. That's going to be dx dt times 32,000. I was going to write the, well, I tell you what, let's do this. This will be better. 32,000 16,000, and that is over the denominator squared. So that's the derivative of this, and then remember, times dx dt. Let's write it like that. I like that better. All right, so basically what we have here is we've got df dt is equal to, let's see, what can we do? That's going to be negative 16,000 over square root of x over 3 plus square root of x squared dx dt. And so we've got df dt is equal to negative 16,000 over square root of x times 3 plus square root of x squared dx dt. All right. So what do I have there? Well, this is over 1, right? So remember, this is negative 16,000 over square root of x times the reciprocal of that times 1 over 3 plus square root of x squared. And see, that's how that square root of x gets in the denominator. Okay. All right. Now, that's what we're wanting to know. We want to know is at what rate is the fish population changing at this time. So you can see we're looking for df dt. So the df dt, that's actually what we're looking for. So we need values for dx dt, and we need a value for x. Okay. So let's see what we've got here. Dx dt, that's the change in x. It's increasing at a rate of 1.4. So we know dx dt is equal to 1.4. And then we need a value for x. So let's see if we have anything that tells us that. A lake is polluted by waste from a plant located on its shore. A college determined that there will be F fish of a certain species in the lake, where F is equal to this. When there are 4,000 fish left in the lake, the pollution is increasing at that rate. So they're telling us when F is 4,000. So when F is 4,000, that's when we want to know what X is. So that's going to be 32,000 over 3 plus square root of X, right? And so what does that give us? That gives us, let's see, 4,000 times 3 plus square root of X equals 32,000. So 3 plus square root of X is equal to, I'm going to divide everything by 4,000, trying to squeeze this in. So that's going to equal 8. And then subtract 3 to both sides. Square root of 8. Square root of X is 5, which means X is 25. And so here's my values to plug in. I'm going to plug in 25 for X and 1.4 for dx dt. So I've got df dt is negative. That's negative 16,000 over, was that square root of 25 times 3 plus square root of 25 squared times 1.4. And that gives me an answer of about negative 70. And so what does this mean? It means that the fish population is decreasing, right? Is decreasing by what? 70 fish per year. And that's what they're wanting to know. I don't think that went off the screen. Nope, it didn't. Okay, so this is our last problem here. All right. So it says when the price of a certain commodity is P dollars per unit, the manufacturer is willing to supply X thousand units, where we have X squared minus 2X square root of P minus P squared equals 31. How fast is the supply changing when the price is $9 per unit and is increasing at the rate of 20 cents per week? Okay. All right. So it says when the price of a certain commodity is P dollars, the manufacturer is willing to supply X thousand units, and they want to know how fast is the supply changing. So X represents the number, and the supply, the number of units we have in supply. So we're actually looking for, we want to find dx dt, right? And let's see, what else did they give us information? Yeah, when the price is $9, so P is 9 because it's P dollars, and is increasing at the rate of 20 cents per week. So that's how fast the price is changing. So dP dt is 0.2, right? 20 cents, we got to put it in dollars, okay? If you plug in 20, then it's like you're plugging in $20. And the other thing that we're going to need to know, it looks like we're probably going to need to know what X is also, right? So how do we find X? Well, they tell us we want all this information when P is 9. So if we take 9 and plug it in, let's see, we've got X squared minus 2X square root of 9 minus 9 squared equals 31. So X squared minus, what is that, 6X minus 81 equals 31. So X squared minus 6X, what is that, minus 112. 112 equals 0. That's a 1 there. And so this will factor into, let's see, what will that factor? X, and how about plus 8 minus 14? So we get X equal negative 8 or X equal 14. And so we know it's not going to be the negative. And so we get X is equal to 14. So this is part of the information that I'm given, X equals 14. And we're going to look for dx dt. So we've got to differentiate this with respect to t. So what I'm going to do is, if you're copying this, pause the video and copy it, because I'm fixing to erase it so I have room. Okay. See, all it is when you're doing this, you're looking, okay, what do I need to find? And so now I need variables to plug in for everything else. And that's what we did there. We just found out what x is. All right, so let's take the derivative of this thing. Hope it's not going to be too bad. Hopefully it won't. All right, so we've got 2x dx dt, right? Minus, now I've got the product rule here, don't I? So I've got, and so this, I'm going to need to put that in parentheses. So I've got derivative of 2x is 2 times dx dt times the square root of p, the derivative of the first times the second, plus the derivative of the second. Remember, I showed you that shortcut for finding the derivative of a square root. If you don't like that, if you don't want to use it, if you don't remember it, then just come over here, do square root of p, change it to p to the 1/2, and do the power rule on it. You'll get the same thing. So that's the derivative of the second, and that's going to be times dp dt, and then times the first function, which is x squared. So that's the derivative of that using the product rule. And then that's going to be minus 2p dp dt equals, and the square root of 31 is 0. So let's clean this up a little bit. So that's 2x dx dt minus 2 square root of p dx dt plus, and that's going to be, what is that, x squared is that x squared over 2 square root of p times dp dt. It's not plus, it would be minus, right? Okay, everybody, let's back this up. I screwed it up, didn't I? All right, I'm glad I caught it. Let's erase this. Everything's correct. So I did the derivative of this, which is 2 times dx dt. Okay, derivative of 2x is 2 dx dt. That's the derivative of the first function times the second function square root of p. Plus the derivative of the second function, which is 1 over 2 square root of p dp dt times the first function. And what did I do? Like a dummy, I looked at this. The first function is 2x. So that should be times 2x. Sorry about that. All right. It's just when I said times the derivative of the first function, I looked over here, I was looking at that instead of the 2x. Okay, that happens. All right. So I've got the 2x dx dt, distribute the negative, so it's minus 2 square root of p dx dt minus, and that's going to be x over the square root of p dp dt minus 2p dp dt equals 0. All right. Now, everything I need to solve for dx dt. So everything that doesn't have a dx dt needs to go to the other side. So I've got dx times dx dt minus 2 square root of p dx dt equals x over square root of p dp dt plus 2p dp dt. And then I factor out a dx dt, and that leaves me with 2x minus 2 square root of p equals x over square root of p dp dt plus 2p dp dt. All right. And I tell you what, from this step to this step, I'm actually going to redo that. And I'm going to write this as plus 2p times dp dt. I'm going to factor out that common factor of dp dt. I mean, why not, right? And so now I'm going to divide both sides by this. So I get dx dt is equal to x over square root of p plus 2p over 2x minus 2 square root of p. And this is times dp dt. All right. So far, that looks pretty good. I don't think I've messed anything else up. All right, so here we go. So what are we doing here? We've got everything up here that we need. So let's just kind of grab this and let's move it down so we don't have to rewrite everything. And now let's just plug everything in. So I'm going to get dx dt is equal to, so that's going to be 14 over the square root of 9 plus 2 times 9 over 2 times 14 minus 2 times square root of 9. And this is all times 0.2. All right, and this is going to give us 0.206. You get to use a calculator, so just pop that into your calculator. All right, now remember, it says that our supply, where is it? X 1,000 units. X is in thousands, okay? So remember that. So it says the supply increases at the rate of 206 units per week. And there you go. There you have it. That's your dxdt. Remember, that's in thousands. So we got to move the decimal 3 places to the right. All right. So let me go ahead and hurry up and do my outro. So I'm going to try to keep it under an hour. All right. So I hope you enjoyed this. Check out my other videos. Give me a like, share, subscribe, comment. And I will see y'all in the next one. Later.